Conductance. You're familiar with the idea of resistance, a measure of how difficult it is for current to pass a component. Sometimes it's more useful to think of conductance, a measure of how easy it is for current to pass a component. Something with a high conductance would have a low resistance, and vice versa. Resistance is given the symbol R and is measured in ohms. Conductance is given the symbol G and is measured in Siemens. We know that resistance in ohms is equal to the potential difference in volts divided by the current in amps. In symbols, R is equal to V over I. Whereas conductance in Siemens is equal to the current in amps over the potential difference in volts. In symbols, G is equal to I over V. So you'll see that conductance is just the inverse of resistance. So we can write that resistance is equal to 1 over G, or equally, conductance is equal to 1 over R. Here we have a simple circuit with two resistors in series. However, you'll notice I've called them G1 and G2 as I'm considering them as conductors in terms of how easy it is for current to pass through them, rather than as resistors in terms of how difficult it is for current to pass through them. You know that in a series circuit the potential difference from the supply is equal to the sum of the potential differences across the components. So I can write Vt is equal to V1 plus V2. But V is equal to current over conductance. And so I can substitute for V in these terms to get that the total current over the total conductance is equal to the current through conductor 1 divided by the conductance of conductor 1 plus the current through conductor 2 divided by the conductance of conductor 2. But as the current is the same all around a series circuit, the total current is just the current through conductor 1 and also through conductor 2. So we can cancel throughout by I to get that 1 over the conductance of the circuit is equal to 1 over conductor 1 plus 1 over conductor 2. The total conductance will always be less than the lowest conductor in the circuit. This gives you a quick check that your calculation is probably correct. Here we have a simple parallel circuit with our two resistors, again considered as conductors, in parallel. For a parallel circuit, the current is shared between the branches, and so we can write that the total current is equal to current 1 plus current 2. The current coming through here is equal to the sum of the currents through the branches. But we know that current is equal to conductance multiplied by potential difference. So I can substitute in this term to give the total conductance multiplied by the total potential difference is equal to the conductance of conductor 1 multiplied by its potential difference plus the conductance of conductor 2 multiplied by its potential difference. But the potential difference is the same across each branch of a parallel circuit, or the total potential difference is equal to the potential difference across branch 1, which is also equal to the potential difference across branch 2. So we can cancel throughout by V to get the total conductance is equal to conductance 1 plus conductance 2. Total conductance will always be greater than that of the highest conductor in the circuit. This gives you a quick check that your calculation is probably correct. Let's just look at a simple example. Whereas to find the conductance of this combination of conductors, we have a 5 Siemens conductor in series with a 10 and 15 Siemens conductor in parallel with each other. So, for the parallel conductors, this combination here, we know that the total conductance is equal to the sum of the conductances, which is just 10 Siemens plus 15 Siemens, a total conductance of 25 Siemens. For the whole circuit, we can now treat this as a 5 Siemens conductor in series with a 25 Siemens conductor. So we can write that 1 over the total conductance is 1 over 5 Siemens plus 1 over 25 Siemens. So this is 5 plus 1 over 25 Siemens. So the total conductance is the 25 Siemens over 6, or about 4.2 Siemens. In summary, for resistors in series, the total resistance is equal to resistance 1 plus resistance 2, and so on. For conductors in series, 1 over the total conductance is equal to 1 over conductance 1 plus 1 over conductance 2, and so on. For resistors in parallel, 1 over the total resistance is equal to 1 over resistor 1 plus 1 over resistor 2. Whereas for conductors in parallel, the total conductance is just equal to the sum of the individual conductances.